students. This video lecture is about Fourier series. This will be the first video lecture on the topic, and in this lecture we will try to understand Fourier series, what it is, where from does it emerge, and what actually do we do with this Fourier series. In order to understand it, we simply start with an example without going into details. Those details can be later on brought in, and we can fine tune all the this discussion later on. But we start with a simple example. Suppose we have this string that is tied at one end to a wall, and at the other end it is held tightly by a person. We imagine the string to be very, very long so that waves are not reflected before we complete our discussion. If waves are reflected from this, all these arguments, they will have to be changed. So we will study only one-way transmission of waves, that is down the string, and we imagine that this wall is so far away that the waves take a long time to be reflected and come back. But before that, we finish our this discussion. So suppose this person, while holding this string very tightly, he then gives it oscillates this end up and down. He takes his hand up and then brings it down, and so on. He starts oscillating it, and as he oscillates this end of the string, a wave travels down the string like this. Okay, like this. This wave can be it is, you can look at the shape of this wave. This reminds us of sine theta. Sine theta has a shape that is similar to this wave. Identical, rather. I cannot say identical because sine theta and this wave can have one difference, that is the amplitude. While a sine theta has an amplitude of 1, that is maximum value 1, this wave can have an amplitude of this greater than 1 or less than 1. So that is the only difference, but the shape is like sine theta. Such a wave is called sinusoidal wave if it is described by a sine function, a simple sine function. Now, even if it is described, suppose the wave shape is like this. Suppose we have a wave shape like this. Instead of that, we have a wave shape like this. Then this shape of the wave can be described by cos theta. Even this wave shape is called sinusoidal. Both sine and cos, they are called sinusoidal. Sinusoidal waves are the simplest waves in nature, and let us now describe some properties of these waves. The important thing that concerns us in this lecture is that we can describe this wave as a trigonometric function, sine theta. That is, for example, if I call this vertical displacement of the string, this is vertical displacement here, this vertical displacement here, vertical displacement here. If I call this vertical displacement of the string as psi, then, and this position along the string by, if I denote it by x is this horizontal position along the string. X tells us about the point on the string. If x is 0, the point of the string is here in my hand, in this person's hand. If x is equal to, say, 1, it is here, x equal to 2, it is here, and so on. You can think of this yourself. Now, this wave displacement, string displacement psi, can be written as a sine kx at a particular time. I will explain this at a particular time, what I mean by when I say at a particular time. At a particular time, I can describe this displacement, vertical displacement, by a sine kx. Now, so far as A is concerned. A simply means, if you don't write it A here, then it means that this wave can have a maximum displacement of 1, because suppose you write it as A psi is equal to sine kx. This means the maximum value of psi should be equal to maximum value of sine kx, but we know that maximum value of sine is 1. This means that psi will have an amplitude of 1. That is not must. It can have different amplitude. So we have to allow for that a different amplitude. We write it here. Say for example, amplitude of this is 10. So I will write psi is equal to 10 sine kx. 10, when I say amplitude of this is 10, I mean 10 centimeter or millimeter. So this is the amplitude. This represents amplitude. Why this sign? Because the shape of the wave is identical to sine. It increases and decreases. The displacement increases and decreases. If the displacement would have been only increasing, then we would perhaps write something as this, AT. If would have been only decreasing with time, with position here, with position along the string. Now we would have been writing it as A by X, something like that. But neither this nor this. The position of the vertical displacement of the string, that is psi, is increasing, then decreasing. Here you can see it increasing, then decreasing, then reversing direction, increasing negatively, then decreasing negatively, and so on. We can say that this displacement, vertical displacement, keeps on increasing and decreasing. Where there is an increase and decrease, like as you have in some rhythmic tones, there is sine and cos. In fact, sometimes one is tempted to say that sine and cos have been sent by God to describe oscillations on Earth, oscillations in the universe, not only on Earth, in the universe. Yes, whenever you look at sine kx and cos kx, you think of oscillation. Think of something oscillation. Okay, whenever you look at these two. Now, let us proceed ahead. Now, what this kx? Because see, the displacement, vertical displacement of the string depends upon the position of the string particles. Here, string particle is here at 0 position. Its displacement is right now. See, one thing that you must have in your mind. This picture of this string is not going to remain. The next moment, the picture will be different. You can imagine that you have taken a snap of the string at a particular time. That means this shape corresponds to a particular time. Next time it will be changed. That's the wave. Next time it will change. For example, let me tell you, right now this particle, say particle A1, let me call it this particle 1, just to show you where I am actually pointing. This particle 1 at this time is at the peak. After an instant of time, it will return. It will be here, then here, and at that time when it will be down, it will be coming down. The shape of the string will change, and not only here. Same will apply to this. Same will apply to this. So shape of the string changes with time. But we are talking about a particular time. So this is a snap of the string at a particular time. Now, the important thing is that, let me clarify one more thing. That is, there is a difference between oscillation and wave. Oscillation or vibration, what you call it. Oscillation and wave. In an oscillation, if you have an oscillation, say it's that of a pendulum. You have a pendulum, and this pendulum is oscillating. It is an oscillator. It is this displacement psi is changing with time. Sinusoidally with time, we write it A sine omega t. That means it increases, then decreases, then reverse direction and increases in that direction, that comes back, and so on. It follows sine curve. It is its displacement follows sine curve. Now, here what you find that in oscillation, displacement varies sinusoidally with time. We will talk about omega later on with time. Now, in a wave, displacement at any point varies simultaneously with two things, with time and space. Both things. It varies with time, it varies with space. Now, right now, you have fixed time. How you have fixed time for this string? You have taken a snap. The moment you take a snap, you are actually arresting time. You are imprisoning it that moment of time in your this snap. Now, this snap at this suppose this snap corresponds to a time say 3 p.m. At 3 p.m. you have taken this photo of this string, and at that time, so this means that the displacement of the string at any point now, the displacement of the string at any point at that time has a constant value of time. That means this displacement at 1, displacement at 2, displacement at 3, displacement at 4, they correspond to a fixed time. Time is fixed, 3 p.m. And while time is fixed, vertical displacement is not fixed. Time is same for all these particles, but their vertical displacements are not same. This means that vertical displacement here is changing with space. It is changing with position, or we can call that space as well. Yeah, you get the vertical displacements are changing with space, right? With x. Now, if you now relax this condition that you don't keep time fixed. Now, suppose you watch 1. You now fix x. Let us now fix x. Fix how to fix x? Focus only on one particle of the string. Let me focus on 1. When I focus on 1 only, I don't look towards 2. I don't look towards this left of 1. I simply look at 1. Only 1. My focus is at 1. This means that position is fixed. 1 has a fixed position. Now, but the displacement of 1 is not fixed. It changes. If I look at 1, I will see 1. Right now I am seeing it at the top. Then I will see it coming down, then going below this mean position, going to the negative this position, negative peak, and then coming back and keeping on doing this thing. This means that 1 will be oscillating, continuously oscillating between this and this, continuously oscillating between these points. This means that its displacement is changing, but now it is not changing with position, because position of one particle is fixed. So with what it is changing then? It is changing with time. So you in a way you have two variations, simultaneous variations of something. Here in this particular view, it is quite easy to identify what that something is. That something is vertical displacement. This vertical displacement changes simultaneously with two things. With position, x is changed sinusoidal with position. That means from point to point it changes, and it changes sinusoidally. With time, at one fixed point, it changes sinusoidally with time. So we have two sinusoidal variations in a wave. If you have single sinusoidal variation, it is not a wave, it is an oscillation. A wave is characterized by this thing, that wave is basically a dance of space and time. You have two variations bound together, one with time, one with space. Now, coming back to this, if there is a variation with space, you write x. You write, for example, sine x. Why this k? You write t. Why this omega? Yeah, you can check it. Normally, we are told that sine, cos, these are defined for angles. So when I write sine t, this is not the proper way of putting an argument before sine. We have to sort of convert it into the angle. How to convert it into angle? we multiply it, we will multiply it with a constant, say we will multiply with a constant omega. Omega is a constant, such that when omega multiplies t, this quantity is an angle, is an angle. How do we know it is an angle? You know that omega basically is angular speed. Angular speed is that is theta by time. Angular speed is theta by time. Okay, by cross multiplication, theta is equal to omega t. So this omega t is basically angle. Now, but omega should be constant. Why it should be constant? Because if you want this displacement to vary sinusoidal with time, then omega should not itself vary. It should be constant. Let displacement vary only with time. So omega is a constant of this motion, is a constant of this motion. And similarly, here when you have to convert here displacement into angle. Now, displacement into angle cannot be converted with the help of this omega. Just let us see here. Suppose we had a sine omega t. Basically, we bring this omega here to convert t into the angle. So we wanted an angle. We had time, but we wanted an angle. So we multiplied it by omega. Okay. Now we have an angle. Okay. But there is a bonus that you get. What is that? Omega has been actually brought in as a constant that converts t into angle, but it has a meaning as well, physical meaning. What it is? It is a measure of frequency of the oscillation. How do I know it is measure of frequency? Quite easy. Quite easy. Suppose you have a pendulum like this. Sorry, this is pendulum, not upside down pendulum. You have a pendulum like this, and this pendulum is oscillating. Suppose it is oscillating like this, going there, here and there, so on. Now, when pendulum is oscillating, you see, suppose it is displacement, it is position, it is displacement. It repeats after regular intervals of time. Suppose at a particular instant t1, the pendulum passes through this point in this direction, in the positive x direction. It is not x. Unfortunately, it is a curve. So you can see a positive right direction. Positive right direction. So at t1, suppose this displacement is psi 1. So displacement is psi 1 at a sine omega t1. T1. You don't change omega. You don't change a because they are constants. Now you have this situation now. Suppose then the pendulum goes, the bob goes there, comes back, passes through this, goes towards this position, this say negative side, and comes back from the negative side and passes through the origin. And when it passes again through this position, it is displacement repeats. It is displacement repeats as soon as it passes through this position. But the time will be t2, a different time. First time it passes through this time was t1. Now time is t2, but the displacement is same. That means I can write psi 1 is equal to a sine omega t2. Omega t2. Now this means I can equate these two. I can write a sine omega t2 is equal to a sine omega t1. Now a cancels. Now you have sine. This is basically an angle. This is sine theta 2 is equal to sine theta 1. Sine theta 1. Now if sine of two different angles is equal, the only possibility is that the two angles must differ by some integral multiple of 2 pi. The minimum difference should be 2 pi. Because after 2 pi, things repeat. So if you have, say, suppose this situation, this is the revolving line OP, angle is 30 degree. Now if you give a 2 pi rotation to this revolving line, 2 pi rotation, that you will come back to this after 2 pi. It is same situation, same. So theta 2 minus theta 1. But what is theta 2? Omega t2 minus omega t1 is equal to 2 pi. Or if we take omega common, let me write it here. Taking omega common, you have t2 minus t1. t2 minus t1 is equal to 2 pi. But what is t2 minus t1? t1 is the first instant when the ball passes through this point. t2 is the next instant when ball passes through this point. This means that t2 minus t1 is the time period of the motion, because after this time the motion repeats. So basically this is time period of the motion. So we can write omega t is equal to 2 pi. That gives us omega is equal to 2 pi by d. This important relation we will be using. And then next we have omega is equal to 2 pi 1 by t, that is frequency. As you know, 1 by t is frequency, inverse of time period is frequency. So this, you can see from this that omega is directly proportional to frequency. That means omega is a measure of frequency. Greater the frequency, greater omega. Lesser the frequency, lesser this. We use omega in place of frequency. Actual frequency is new. Of course, it is new, but omega can be used in its place. It's something like this: that suppose you have a brother whose name is X. So you have in your home, you have a room where there is a picture of your brother on the wall. You have some photograph on the wall of your brother. So while sitting with your friend in that room, you point towards that picture and tell him that he's my brother. So this photograph can be used in place of the actual brother. Omega is a sort of photograph of omega nu. Actual frequency is nu, and omega is the brother of that nu. So we usually use, what we do, when we speak of omega, we mean frequency. Although we keep in our mind that we have to multiply it by 2 pi to get the actual frequency. These things and others we will be using. So when I write psi is equal to a sine omega t, omega is always equal to a sine omega. In place of omega, you can write 2 pi nu t, while nu is the frequency. And frequency, we know frequency is number of oscillations per second. This is variation. So this was about this we should say temporal variation in wave. Temporal means with time. This is the temporal aspect, that displacement varies sinusoidally with time. Now let's go to spatial aspect. Spatial means with space. Spatial aspect of variation. Spatial aspect. In spatial aspect, we have psi is equal to a sine kx. Now instead of starting with this, why not start with this? We can obtain this variation of psi with space by simply copying this. How? Say psi is equal to a amplitude of the wave is as usual. Amplitude sine is 2 pi. Okay, this is a constant, and we expect this to be in special this expression as well. Now the difference. Here we have nu. Nu is number of oscillations per second. Here I will use nu bar, that is number of oscillations per centimeter. That means this is number of waves per unit length. Just as nu is number of waves per unit time. This is number of waves per unit length. There you have per unit time. Here you have per unit this length. time, space and length. You can see space and time. And lastly, here I have this time, this variable time. Here I will have variable position. So this is the all this expression for spatial variation, sinusoidal spatial variation, that I copied from this sinusoidal temporal variation. So what is this? This is called wave number. This new bar is called wave number. It is the number of waves per unit length. Just as we write 2 pi nu in 2 pi nu is replaced by a single constant omega. Similarly, 2 pi nu bar is replaced by a single constant called k. You can call, just as omega is angular frequency, we call it angular frequency, although there is nothing angular always. There may be some special cases where there is some angular aspect, but it is not must. For example, think of voltage, AC voltage. You cannot even imagine of an angular frequency of an AC voltage. That is nonsense, purely nonsense. Angular this frequency of an AC voltage. So, but you know why we are doing this thing. Now, similarly, you have here this angular wave number. This is K is angular wave number. It is a very important quantity, we use in quantum mechanics and other fields of physics. This is the spatial aspect, that is the temporal aspect. So I can write, finally, I can write A sine omega 2 pi by 2 pi by k. Sorry. 2, I can write 2 kx. I can write kx. K for 2 pi nu bar. We have to keep these all formulas at one place. We will write it here. For example, I will keep this in this corner. K is equal to, I have written K for 2 pi nu bar, angular wave number, a measure of wave number. Now then I have omega is equal to 2 pi nu. Now there is one more expression for omega. For omega you have, for example, here you have for omega 2 pi by t, this time period. Similarly, we have there k is equal to 2 pi by this space period lambda. That is lambda. I have written lambda, rather 1 by lambda for nu bar. How can I write 1 by lambda for nu bar? Quite easy to see for you. You have nu bar is number of waves per unit length, per unit space or length. Say per unit length, number of waves per unit length. What is lambda? Lambda is the distance in which one wave is fitted, or one wave fits in this distance. Lambda contains one wave. You can see it here. This is lambda. We call it space period, just as we have time period. After time period, wave repeats. After space period, wave repeats. So it is analog of this T, capital T, time period. Now lambda now is equal to lambda is the distance in which you have one wave. That means you have, say, for example, I should start like this. Distance, number of waves in lambda distance is equal to 1. By definition, it is called 1. Number of waves in one distance, that is 1 by lambda. Number of waves in, say, yes, so that this is what I wanted. This is number of waves in one distance, that means unit distance, that is 1 by lambda, and this is what we call wave number. So wave number is 1 by lambda. Number of waves per unit distance. So I have, till now I have this situation. I have not this situation, and I will keep these things with me. That is nu bar is equal to 1 by lambda. These formulas we will be using They will be important for us. Now, all this physics now that we have completed, we will now put into action. But before we put it in action and show you what Fourier series is about, before that, I need one more thing. That is a simple thing. Suppose you have 1 by root 2. You can think of 1 by root 2 as 70%, approximately 70%, or 0.7 or 70%. How? This is simple, by division. This is 1 by root 2 is approximately equal to 1 by 1.4. Approximate value of 1 root 2, 1.4. That is 1 divided by 14 by 10. 14 by 10. There's 2 5s are, 2 7s are. Divide 5 by 7. 0.077 are 49. So it is 0.7 approximately. Approximately 0.7. Keep it roughly. Remember that 1 by root 2 is 0.7. So suppose you have one more thing, that is, I will need, in order to explain to you what this Fourier series is about, I will need value, often I will need this value sine pi by 4. Sine pi by 4 is sine 45 degree. 45 degrees 1 by root 2, that is approximately 0.7. Same is the case with cos. Cos pi by 4 is also the same, 1 by root 2. Now, one more thing before I embark upon that this concept, that is, suppose I have this here you have time, here you have this time, and this is this wave displacement, time and this or space. I am going to use space and this now. Suppose, and this is the wave. This is the wave. Okay, this is the wave. Okay, now the distance in which one cycle of the wave is completed is called lambda. This is lambda. Then this will be lambda by 2. This will be lambda by 4. This will be lambda by half of this will be lambda by 8. What I will do, I will divide this lambda into these pieces, lambda by 8, lambda by 8, then again lambda by 8, then lambda by 8. How many lambda by 8 have I now from this point to this point? 1, 2 lambda by 8. 2 lambda by 8 is same as lambda by 4. 2 lambda by 8. See, 2 lambda by 8. So 2 ones are 2 fours are lambda by 4. So lambda by 4 is 2 lambda by 8. Now then 3 lambda by 8. 4 lambda by 8. See, 4 lambda by 8. 4 twos are. That is lambda by 2. This is lambda by 2. So 4 lambda by 8. 5 lambda by 8. 6 lambda by 8. 7 lambda by 8. 8 lambda by 8. That means I will divide this lambda into 8 divisions. One more thing, that is, suppose I take this as 10, amplitude as 10 as an example. I'll take it 10. Now, what will be the value of this wave at this straight at when displacement, position is equal to lambda by 8. What will be the displacement at that? You can easily check it. The wave is itself described by sine. So the formula for this wave is psi is equal to 10, because you have chosen amplitude as 10. 10 sine kx. Now I want value of psi at pi by 4, at lambda by 8. At lambda by 8. I want value of this lambda by 8. I will use this 10 sine, and I will do one more thing, that is, I will change k into lambda. Now k is equal to, you can see it here, 2 pi by lambda. So I will write it 2 pi by lambda into x. What is x? What is the x here? It is lambda by 8. Lambda by 8. So lambda and lambda cancel. You get 2 ones are 2 fours are. That is 10 sine pi by 4. What is that? 10 sine pi by 4 is pi by 4. That is, you have seen sine pi by 4 0.7. 0.7. This will be simply 7. So value of this is 7. What do we learn from this? We learn that a sinusoidal wave rises to a value of 70% of its peak value. it rises to a value of 70% of its peak value in lambda by 8. And in next lambda by 8, it does not rise that much. It rises only by 30% because perhaps it is tired. Its rate of change falls. And then when it falls, see, at 1 lambda by 8, its value was 7. At this 3 lambda by 8, at 3 lambda by 8, because it is 1 lambda by 8, this 2 lambda by 8, and this 3 lambda. At 3 lambda by 8, I mean this point where I am just now pointing you towards. At this point, what will be its value? It will be, at this point, its value will be, we can check. Yes, let us take it. We can check. You can yourself see this value and this, they are symmetrically placed. This means it will again be 7. Now, if I mean this. Let me show you at point A. Its value will be exactly same as at this point where I have shown 7. Why they are symmetrically placed? Or even if, and suppose you don't agree with me and you say no, sir, show us, and I can show it. That is, suppose I want psi 3 lambda by 8. Psi at 3 lambda by 8. 1 lambda by 8, 2 lambda by 8, 3 lambda by 8. That is 10 sine 2 pi by lambda, in whose place? K, in place of K. Now X position, value of the position is 3 lambda by 8, 3 lambda by 8, 3 lambda by 8. Lambda cancels. You get 2 1s or 2 4s are. So you have 10 sine 3 pi by 4, 3 pi by 4. Now 10 sine 3 pi by 4 can be written as pi minus pi by 4, because 4 into pi, that is 4 pi, 4 pi minus pi, that is 3 pi by 4. Now this will be 10 sine, because sine has 180 degree in front of it, so sine will remain sine, and pi by 4, but we have to check what will be the sign of sine. That means whether it is positive or negative. This is second quadrant perhaps. Yes, pi minus pi by 4. In second quadrant, sine is positive, so it is positive. So it will be 10 into sine pi by 4. Sine pi by 4 is 0.7. That is 7. So it is 7 here. Again, you see it is 7. Now the interesting thing is that at what we saw this thing, we saw at x equal to x and value of psi. Now at x equal to 1 t by 8, 1 lambda by 8, at x equal to 1 lambda by 8, 1 lambda by 8, that's this value of psi was 70%. At x equal to 3 lambda by 8, that means point A, at point A, x equal to 3 3 lambda by 8, 3 lambda by 8, again 7. X equal to 5 lambda by 8, check it and you will find again 7, but it may be negative. Yes, of course, at that it is this again 7. If you have doubt, you can calculate. You have this psi equal to 10 a sine. This will be, now this is 5, it will be 2 pi by lambda into x. X is lambda by 8. 5 lambda by 8, sorry. 5 lambda by 8. 5 lambda by 8. Lambda cancels. 2 1s are 2 4s are. And psi equal to a sine. You have 5 pi by 4. That is equal to a sine. Pi plus pi by 4. Pi plus pi by 4. That is equal to sine. A sine. Sine will remain sine, but pi by 4. But sine will now change. That is because it's third quadrant, and in third quadrant sine is not positive, sine is negative, so it will be minus here. So it will be minus 10 a 10 sine pi by 4, that is 7, that is minus 0.7, sorry, this is 0.7, that is 7, minus 7, you can see minus 7. In fact, you will find one trend, that is at all odd multiples of lambda by 8, you will have either 7 or minus 7. odd multiples, that is 7 lambda by 8, again it will be minus 7, then at 8 lambda by 8 it will be 8 lambda by 8 will be not odd multiples only, and odd 9 that we don't require because we require only up to 8. This is 5th, 6th, 7th, 8th. 8th is here. With these things, let you prepare yourself now with prepare your mind now for understanding what Fourier series is about. Now I'm going to use all this, and then this I have, for example, suppose I have a string in which there are two waves simultaneously. Two waves in a string. One wave, I will show first that wave, but I will have to keep track of things. So I will do one thing. I will take lambda here. Lambda, let me first draw it. This is wave. See, I have taken, if you can see it clearly, that the amplitude of the wave has been taken as equal to 2 this spacing between rulers, these rules, sorry. You can see this is the space between these two lines. I have taken two such spaces as the amplitude of the wave. Now this is the amplitude of the wave. This is the dotted, that is amplitude of the wave. Now I let me say that it is 10. Suppose it is 10. Amplitude is 10. So this means that one space will correspond to 5 centimeter, for example. If we have units of centimeter. Anyhow, this range from this point to this point, I have one lambda, one wavelength in which the distance in which one wave repeats itself. Now completes. Now I have this wave I will call psi 1, because I am going to combine another wave with it, psi 1. So this is I will divide this whole range of this into 8 these divisions, 8 lines. That is, say first of all, let me draw these lines to keep track of things. I will draw these lines. I'm sorry, I will have shift it. I can shift it. Let us shift it first. Let's keep it here. Okay, now I have now another wave. That wave, but before drawing that, I will do one thing. I will divide it. Till now, I have divided the whole range of lambda into 4 parts. 1, 2, 3, 4. Unfortunately, they are not exactly same. There is some error, but that will not uh, create any problem for us. You now have another wave. But since that wave will have to, yes, its amplitude can be more than that, so I will have to take it from this. So it is like this, and what I'm going to do, I'm going to divide this gap, lambda by 4 gap, into 2 parts. I have this lambda by 8. Now lambda by 8. Okay, then another, I will divide this also into 2 parts. And then this also in 2 parts. You can, if you like, you can use rulers, and you can then do it at your place. Well, the ideas will be clearly conveyed. You can see it yourself. Psi 2 is equal to this. Psi 1, psi 2. Now, the second wave that I am going to show you, will have a frequency that is double of this first wave. That frequency will be double. Just a minute. Now frequency of this will be uh, double, as I told you. That means it will go up. Amplitude is same, amplitude same, frequency double. It is double frequency. Yes, it is like this, then this, then this, and lastly this. Yes, okay. Now these are two waves. Now the expression for this, oh sorry, the expression for the first wave. Now expression for the first wave is this. I will write it here. Psi 1 is equal to a, that is 10. A is 10. A sine k1x, k1x. Okay, k1x. It has one wavelength. That is why k1, it has different k1. And this expression for this will be psi 2 is equal to a sine k2x. Why this k is different? Because wavelengths are different. And k, as you know, k is equal to 2 pi by lambda. 2 pi by lambda. Wavelengths are different, so k's are different. Okay. Now, suppose these two waves are in the same string. They are in the same string. How? You can think of this. Suppose you have a string like this, and two boys are holding this string in their hands. This hand of one boy and this hand of another boy. A and B are two boys who are holding this string taut. That means tightly, so that there are no wrinkles in it. Now, no this loose. It is not loose. It is not to be loose. It is to be kept held tight. Now, suppose A tells B, you just hold it. Don't move your hand. Just hold it tightly. I will give a jerk to this string here. So A gives a jerk to this. A takes his hand up. So the hand goes up, and the shape of the string becomes this. This A, this is A, this is B. When A comes down, this crust that is produced here, this crust, it does not come down. It slips ahead. It slips like this ahead. That means after, when A is back at its position, the shape of the string is this. At that instant is this. It's not going to remain like that. This will now, next moment, this will be here. The shape of the string next moment will be this. Sorry, it will be here. Shape of the string is now here, and so on. This crust will travel along this string in the forward area, in towards right. Okay. Meanwhile, what happens is that as the crust travels this way, meanwhile now, when A is back at its position, when A is back, sorry, when A is back at its position here, and the crust is like this, B tells him, now B asks A to hold his hand. Don't do anything. Now B gives a jerk to this. B has two options. B can first go up and then come down, or B can first go down and then come up. If B goes first up and then comes down, he will produce a crust. That crust will travel towards this crust. And let us first analyze that. When the crust from the B travels towards this crust, somewhere they meet, not that they will not meet in the middle. They will meet here towards nearer to B, because it must have traveled more distance. Now they meet here. Now, when crust from this comes, what does this crust want to do to this point of the string? This crust wants to lift that point up. And what will this crust want to do to that point? Lift up. The two together, if they meet here, the two together will lift it double up. That means the waves will add here. But on the other hand, if B had first gone down and then come up, then the wave, that the pulse that we would have generated would have been a trough. It would have been trough like this trough. And this trough, when it would go and meet this, they would cancel. Waves have this beautiful property of wave plus wave is equal to zero wave. It is possible in waves. Wave plus wave is equal to zero wave. Sorry. Wave plus wave is equal to zero wave. Okay. So you have this beautiful property of waves. Wave plus wave is equal to zero wave. Two waves can give zero. Now, wave plus wave can also add. They can give double wave. In fact, that is actually, anyhow, we won't go there. Now, this beautiful property of waves. Now, you can imagine yourself. Suppose now A and B keep on vibrating continuously. Instead of giving pulses, they keep on vibrating. One with this frequency, another with this frequency. The shape of the resultant wave there is what we want to see. What will be the resultant wave there? Okay, now resultant wave. Here I will show you resultant wave. Psi. Let me call that psi. Now this resultant wave can easily be found. How? You can see yourself. It is now quite easy for you to understand how this resultant wave can be found. See, at zero time, at zero, this is x here. I'm sorry, it is not time, it is x. It is x. We're more familiar with temporal variations. That is why it slips out of our mouth. So you have 0 x at zero position of the string. At zero position of the string, displacement due to first wave is 0, due to second wave is 0. 0 plus 0 will be 0. Resultant displacement will be 0. At lambda by 8, now this is lambda by 8. At lambda by 8, this wave is at top, that is 10. Its value is 10. Its value of this is 70%. 10 plus 7, that means amplitude, this displacement here will be 17. 5 plus 5, 10 plus 5, 15, 17 somewhere here. 17, this is the resultant displacement right now you have. Now 10 plus 7, I have simply added them because they are on the same side, both are positive. That's why I have added them. Now next, lambda by 8. Look at lambda by 8. This is lambda by 8 corresponding to this lambda by 8. You can see at lambda by 8, go straight up and see this is 0 and straight, that is 10. That means the two added together will be 10. So I will have this here 10, 5 plus 5, 10. So this will be 10 here. After that, next, this will be minus 10. This is minus 10. Okay, then straight go up and see that is 7. That is 7. 10 minus 10 plus 7, that's minus 3. Minus 3, it suddenly goes down to minus 3 is there. It was here 0, 10, and now minus 3. Minus 3, so it goes something like this. It goes down to minus 3. Now, then to next moment, we have this 0, and this 0. Both 0. This and 0, this 0. So next, this will be 0. 0. Okay. Then this will be next. This will be 7, minus 7. Minus 7 now. This is plus 10. 10 minus 7, that is plus 3. Plus 3 here. Next moment, it's plus 3. And then next moment, it is here minus 10, minus 10. Okay. Here it is 0. It is 0. So it will be minus 10. Minus 10. That means it will go down and go to minus 10. Okay. Now next, it will be here minus 7, here minus 10, minus 7, minus 10, minus 17. So it will go down to 7, minus 7. This is 5, 10, 15, minus 17 here. Minus 17. And then, lastly, this is 0, and this is 0. Look at this wave, this psi, this psi. You can see its shape. It's not sinusoidal. It cannot be described by a sine. Not at all. No way you can describe it by sine. This non-sinusoidal wave is, but it too is periodic. Next, had I drawn it, some more these cycles, if I had included, you would find that this pattern will now repeat. This the same pattern will repeat now towards right now. So this wave is periodic. This too is periodic, just as these were periodic. And one more thing that is very important. When you combine two waves of different periods, you can see has one period, lambda. This has a smaller period, is lambda by 2. Now, the resultant wave, which is formed because of these two, has the period of the longest period. What is the longest period? Longest period is lambda, so period is lambda, because you can see it doesn't repeat in lambda by 2. It will repeat after this now. After this, it will repeat. So this has a period of lambda by 2. Whose period does it have? The longest period. Just remember this rule, longest period rule, because when it fits in this longest period rule. Now, one more thing, that is, you saw this periodic function, this periodic wave or periodic function. You have, if I draw it here, some like this, this periodic function was created by superposing these two. I can write it if it is psi. Suppose it is psi. I can write this psi is equal to psi x, which is a position of this function of position. Psi x is equal to a sine k1x plus a sine k2x. Now you can yourself imagine that this aperiodic wave is composed of sinusoidal waves. Two sinusoidal waves go in making this periodic function. If you now, suppose you do one more thing that needs a little bit of patience. You add a third wave. You add these two waves and then third wave, and combine them like as I did these two waves. You will find a different function, different shape. Again periodic. That too will be periodic. But that will not be this shape. That will be different shape from this. That different shape can be similarly thought of as being composed of three sinusoidal waves. In fact, what Fourier did, to say that it was done actually by Fourier. Fourier was a great French mathematician, but in fact it was previously done. What Fourier did, he put this in the application, this dogma. That means he was the person who made it highly applicable to physics, especially heat equation. We have heat equation there, and wave equation. So Fourier, all credit does not go to Fourier, but ultimately it was his name that got associated with this. We have, what now is Fourier saying us? Yes, that is, now we can understand it easily.